Dear students, today we are going to discuss about the primary constants and secondary constants of the transmission line. So before that, we should know what is the difference between lumped parameters and distributed parameters. Okay, so lumped parameters where the resistance, inductance and capacitance values which are individually concentrated or lumped at discrete points in the circuit, right? So whatever we studied in that circuit theory, right? So those circuits and the parameters used are lumped parameters. But in transmission line, we should have distributed parameters, which means that the resistance, inductance and capacitance values are distributed along the circuit. Okay, so and for each incremental length of the circuit, which have their own values, and concentration of the individual parameter is not possible in distributed parameters. So in transmission line, so the parameters are distributed in nature. Okay, so the first thing, this resistance, conductance, inductance and capacitance, right? So these four are called primary constants of the transmission line, right? So apart from this R, G, L and C, right, some other constants are there in transmission line. So characteristic impedance, propagation constant, attenuation constant and phase constant. Okay, and these four are called secondary constants. So why it is called secondary constant means, so these constants are fixed at one particular frequency but change their values as the frequency changes. So hence these constants are called secondary constants, right? So for all these values, right, it will depend on omega. It will depend on omega, right? So omega, which is nothing but 2 pi f, right? So it depends on the frequency. These four values will depend on f. So for one particular frequency, it should be fixed. If we change the frequency, means the values get changed. Hence it is called secondary constants, right? So the next topic is relationship between the primary constants and secondary constant, right? So for that we should consider one transmission line, right? So of length L. Okay, and this short line can be represented by some symmetrical T network. So why should we prefer this T network? Means for our easy calculation, right? So if you are taking one incremental length, so normally in transmission line, right, so we should have the impedance, right? So we should have the total impedance as Z1. So we should separate this as Z1 by 2 and Z1 by 2, right? So here consider one resistance, that is Z1 by 2, and here it is Z1 by 2, right? So when we add this, here is Z1, right? So this is continued throughout. This is continued throughout the length, right? So continued throughout the length. So if you see, this is Z1 by 2 and here is Z1 by 2. Okay, fine. So if we take the total series impedance, right? So here, so Z1, which is nothing but R plus J omega L into total length is L. So total length is L. Then this, right? So parallel impedance. So 1 by, it is represented as 1 by G plus J omega C into L. This is parallel impedance of the T section. So generally the total series impedance per unit length. If it is per unit length means then this L is equal to 1, right? So Z is generally denoted as R plus J omega L, and the total parallel impedance per unit length is denoted by pi, which is nothing but G shunt, right? So G plus J omega C. So we should remember these two values, which is very important for calculating the characteristic impedance, right? as well as the propagation constant. So when you are considering this is the characteristic impedance, the definition for characteristic impedance is the characteristic impedance of the line is the ratio of the positively traveling voltage wave to the current wave at any point on the line. Okay, so and it is denoted by the letter Z0. Okay. Then the difference between what is infinite line and finite line. Okay, so for infinite line, if you are taking infinite line, right, here we should see, we should have one voltage source and current source, right, a infinite line, right, so it goes on. So the parameter, right, so Z0, so which plays an important role in the analysis of this particular line. So what is the important properties when we are dealing with infinite line means, right, so as the line has infinite length, then there is no waves, right, will never reach the receiving end and hence no reflection at the receiving end. So this waves is nothing but no standing waves, right? Okay, so and hence no reflection if the line has infinite length. The complete power will get applied at the receiving end is absorbed by the line. This is the concept of infinite line. So as the reflected waves are absent, then the Z0 at the sending end will decide the current flowing, and current will not be affected by the terminating impedance ZR. So the next concept is short line or finite line. So if we are taking the practical line which having some finite line, finite length, so this one, right, so this is the finite line. So I will cut this portion, right, and here also the characteristic impedance is measured as Z0, right. So now AB is the short section from the electrical point of view. Okay, the impedance at the terminating end of section AB must be Z0, right, correct. So this is simplified as Z0. Okay, therefore the properties of such a line will be exactly same as that of the infinite line, right. So what is the condition means a finite line which is terminated in its characteristic impedance which behaves as the infinite lines. So this means that there is no reflection, right. So this is very very important, right. Here we should have an infinite line. If we change this as a finite line, okay, this is the characteristic impedance. At any point the characteristic impedance is Z0. So here also it is Z0 and here also it is Z0, right. So for finite line which is also terminated in characteristic impedance will behave as the finite line. So therefore the condition that if, so for no reflection when ZR is, right, not equal to Z0, right. So if it is not equal to means then we should have reflection, right. If it is equal to means no reflection. Okay, so this is the condition of finite line, and finite line is otherwise called short line and another one is infinite line. Okay, so the next topic is determination of Z0 in terms of primary constants. We should derive the part and find out what is the Z0 value. So consider the same T section, right, and here the characteristic impedance is Z0 load, okay, which is terminated finite line which is terminated by Z0. Okay, so hence the T section is Z1 by 2, Z1 by 2, and here the impedance is Z2 and the input impedance which is also equal to characteristic impedance. Here we are going to calculate this input impedance, right. So first these two things are series impedances, right. So this is 2 in series. So Z0 plus Z1 by 2. Then that answer will be parallel to this Z2. Okay. So parallel. Then it is series with this Z1 plus 2. Okay. We should calculate this. Right. So if it is parallel means, so multiplying these two impedances divided by addition. Okay. So Z2 into Z0 plus Z1 by 2 divided by Z2 plus Z0 plus Z1 by 2. So here we are going to take LCM, right, and here you should multiply, right. So if we do that mathematical and solve, right, here this 2 is Z0 and this term will get to the left side, and in the right hand side we should get multiplied. Okay, so cancel whatever possible. Okay, so the remaining final expression is 2z0 square, which is equal to 2z1 z2 plus z12 divided by 2, sorry, z1 square. Okay, so suppose z0 square is equal to this 2 get here, right, and this is the final equation. If we take the square root, z0 is square root of z1 square divided by 4 plus z1 z2. Okay, if in terms of primary constants. So we already know what is z1 and what is z2, right? So what is z1? So z1 is r plus j omega l. What is z2? What is z2? 1 by g plus j omega c into L. This is L and here it is L. Okay, so when we substitute these two values, right, so here it will get squared the values, and here the L term it get cancelled. So this assumption, so we should assume that, right, the length of the line is small, right, and L tends to 0. Okay, so if the L is 0 means then L square is also neglect the term, right? So only we should have root of this term, right? So this term is neglected. This term is neglected. Okay, so here remaining term is square root of r plus j omega l divided by g plus j omega c. So this is very important formula for characteristic impedance, and while calculating the problems also it is very important. So z0, which is equal to square root of r plus j omega l divided by g plus j omega c, and it is otherwise denoted as z0 equal to root of z by pi. If when the frequency is very small, that is omega tends to 0 means, then this is it not here omega cancel, right? So only r by g. Okay, for low frequency. If it is high frequency means, right, so this r squared term is very less than omega square l square term, right? So z dot value is becomes root of l by c, right? So this is nothing but the characteristic impedance for high frequency applications. That is high frequency. So it is studied in the next concept, right? So high frequency means high frequency lines, the characteristic impedance z0 is nothing but root of l by c. Okay, so this is primary constants and secondary constants of the transmission line. So for coming to the secondary constant, we should have Z0, right? So characteristic impedance. So the second one is propagation constant, which is equal to gamma, which is nothing but root of Z into Y. Okay, so which is equal to root of R plus J omega L into G plus J omega C. This is gamma. So alpha and beta is nothing but the real part and imaginary part of this propagation constant. This alpha is nothing but attenuation constant, and this beta is nothing but the phase constant. Okay, so these are all the primary constants and secondary constants of the transmission line. Thank you.